So applications. Okay. So as I was saying, we would all be considered a system of individual particles within a system of particles. Discrete because we are separate particles and we really don't influence one another unless there's contact between us. Now we might be influenced by external fields that act on all the particles separately, but again, we don't interact as a system. We interact individually, and we only influence one another within the system unless we have physical contact at some point. So that is considered a system of discrete particles. Now, as it turns out, it is useful to describe the system as one particle. And the way that we do that is we define that particle as the center of mass. Center of mass. And if we can figure out where that center of mass is, then the entire system will behave according to that center of mass essentially abides by Newton's laws as well. And sometimes it might be easier to keep up with that center of mass because it's one particle that represents the whole system, as opposed to having to keep up with all the individual particles as the system changes over a period of time. So pictorially or visually, what I might represent is something like this. So you might have a bunch of different particles, right? And they're just from random places. And maybe at any given time, these all have different motions, different velocities. For example, maybe this is the velocity vector associated with these particles. There. So at any instant of time, this is the direction in which they're moving. Just random directions. Well, and maybe in addition to, so as they move, I tell you what, let's have a slightly different. Let's say that this, well, let's just leave it at that. Now, so we could keep up with all the different particles, or we could figure out an average value of all the particles. So maybe the center of mass. Now, if this were a symmetric object, the center of mass would be the center of the distribution. But maybe the masses are all different masses and they're in different positions, relatively speaking. It's not so symmetric. So at this point, it's not so easy to see where this center of mass might be. But basically, the center of mass is kind of a weighted position. It's an average value of the position of the object, but it's not just dependent upon position, it's also dependent upon the mass. So I don't know, maybe the center of mass might be someplace like right here. So there's two ways that I could figure out what's happening to the system. I could just figure out where the center of mass is and know what its velocity is, at a given instant in time, and then follow that along some trajectory, maybe if it's moving. And if I know that, then basically, even as these individual particles move, I still know like the overall position of the system without having to keep up with the individual particles. So basically, Newton's law shows that the average value of the position of a system of particles abides by Newton's laws and equations of motion, just like the individual particles do. That's not something that you can take for granted. It just so happens that that's true. And because that's true, if I find where that average value of position is, then I can manipulate that or evaluate the motion of that, and sometimes that's easier. So finding that average value is called finding the center of mass of a system of particles. system of discrete or separate particles. So we can say that the center of mass, the symbol for it is R, Cm. R is a position vector. So, and we can say that it's the average value, the average weighted or normalized value, the average normalized value. Well, let's see, this is the I would say it like this: the average value of a system of particles normalized by mass. Normalized. What does that mean? Well, it means it's not just the position. It's the position with respect to, well, I guess by would be the term. It's the position by mass. Remember, by means times. And normalized essentially means divided by an overall value. So to kind of put this in perspective, I could make this a three-dimensional figure. And this goes back to the original example that I was about to give with me standing in front of you in a class. So if I superimpose an axis, a three-dimensional axis over these system of particles, it gives them an arbitrary, relative position arbitrary to space. So let's say I do something like this. Right, so kind of make some three-dimensional picture here. And we can make that, I'll put the z-axis up top. That's the x-axis, y-axis here. All right, so these particles are just arbitrary out in space somewhere, right? Like they're, and so each of these particles has a position vector. We know what that is. We talked about that before, right? Position vector is so like if each of these masses is like a number, then so maybe this is M1, this is M2, 3, mass 4, 5, 6, 7, so on and so forth. Well, each of those particles has a position vector that points from the origin to the particle. The three-dimensional coordinate system, it would look something like that. Right? We'll draw all of them. Like that. So that's R2, R1, R7, so on and so forth. Now, you folks, I think you probably have the age of definitely, you folks are Hogwarts generation. As in, so kids name, the kid wizard, what's his name? What's that movie? Franchise? Oh. Oh, hello? Anybody? What's that thing called? Hogwarts? What's his name of the thing? David Edwards. You know what I'm talking about? Jesus. Are you there? Oh, Harry Potter. Yes.
Yeah.
Thank you, Lord.
Oh.
Harry Potter. That's what I'm talking about. Harry Potter. Right. So Hogwarts is a school where they go. And so they sit, so like say this is Hogwarts, right? We're in Hogwarts, and you're in class and I'm a wizard, and you guys are wizards in training. Which in a way you kind of are. If you think of physics in that way, it's an interesting way to think about it. So if I were there and I were trying to illustrate a system of particles to you, I would say, okay, right now you all are sitting, and presumably you're sitting at the same level. So it's more of a two-dimensional figure where I'm standing on the ground, the floor of the classroom is two-dimensional. And that does represent a system of particles, but not fully. So I get my wand and I just do a little spell, and I call, and we're in those big, beautiful, that place was, they had these big, I forget what the name of the architecture is that building was made out of, but they have these big, beautiful classrooms in that movie with those arches all over the place. So the classroom is huge, it's open. And so I wave my wand, and all of you, distribute vertically at different vertical positions. And me, even myself, maybe I come off the ground, I start to float, to what's it called when you do that? Hover. It's not the word I'm looking for, but you get what I'm trying to say, right? And you're all at various positions. And I pick a particular point in class, let's say the edge of a desk, which could represent the origin. And then I cause a piece of string to be attached to the edge of the desk, and I flick the string to each one of you. So you all are holding the string, and all the strings are attached to the central point of the edge of the desk. Even I have a string. And that would more represent the picture that I'm trying to represent, the three-dimensional picture that I'm trying to represent here, where we have the origin is at a particular point on the, in the classroom. It's our reference point where we're measuring all of our positions. And each of you has a string, and that string represents the position vector of the individual, of each individual person. And so it's this system that we want to try to find the center of mass. Now, each term in the center of mass essentially is going to be, it's as I said, it's a weighted position. It's not just the position R, it's a weighted position that is weighted by by your mass. So each of the terms that contribute to the center of mass is going to be your position, three-dimensional vector R, times each of your individual masses. And if I were to figure out, and remember that's a vector because R is a vector. So just like I've represented here. So I could pictorially do a vector analysis problem where I add all of those vectors together vectorially, essentially, breaking up into components and everything. And if I do that and then add all the components together, then I can find that will give me the average value of the position vector of the center of mass. The object that if we replaced all of our individual positions with a mass that was equal in mass to our combined masses, essentially. But technically, it's a massless position, so we'll normalize. That's what the normalized is. But the term that would be equivalent to the term of the center of mass, equivalent to each of our individual terms, would be the position vector RCM times the total mass of the class. Now, if I then, so that would have to be equal. In other words, by vector analysis, the position vector of the center of mass, RCM, times the total mass of the class would have to be equal to the vector sum of all the individual particles that made up that system. So R1 times M1 plus R2 times M2, so on and so forth, to Rn times Mn. So the right side then would be a vector sum of particles, and I could represent that as a summation of the R sub i's, M sub i's, where I goes from 1 to N. And so therefore, if I then divided through that quantity by the total mass of the system, then that would give me the position vector RCM. So the position is weighted, and what I mean by that is I'm multiplying each individual position by the mass of the object, but then I normalize it by dividing through by the total mass. So the center of mass would then be defined as the entire mass of the system time that is, each individual weighted position, R sub I times M sub I, divided by the total mass of the system. And that is our equation that we use for center of mass. It's just kind of an empirical formula derived by logic of how we would do that. And that's for a discrete system. Now, what we normally do, remember, this RCM is a vector. So what we normally do is figure out each individual component of the RCM and separately, because it's just easier to do that. In other words, RCM, the center of mass, is going to be equal to 1 over M. Well, actually, we can do it this way. It's going to be equal to R CM along the X direction plus R, I guess we'd say RX CM plus RY CM plus RZ CM. If we broke it down, in fact, maybe a different notation, just be X CM plus Y CM. In fact, that's the notation I have in my book. Y CM plus Z CM, right? Where X, the center of mass along the X direction, is going to be 1 over the total mass of the system times the summation of the X sub i's, M sub i's, and the other terms would look accordingly. So YCM is equal to 1 over N of the summation phi equals 1 to N of the Y, is this Y, Y sub i's, M sub i's, and finally X or Z, CM is equal to 1 over M, total mass, summation, I equals 1 to N of the Z sub I, M sub i's. Okay, and that's it. That's what center of mass is. These are the various formulas for discrete particles. And it's somewhat straightforward. We can I'll show you right now. Let's do a problem where I show you how this works. So let's say that we have a system of particles, and I'm going to, just for the purpose of illustration, I'll make this a two-dimensional system, so it's just easier for us to kind of get through it and show the definition. So a two-dimensional system where, where we don't have to worry about the z-axis. So consider this problem. Two-dimensional coordinate system here. Let me try to draw this out so it's so. Need to go up to 4 and 5. Oh, need a bit more room. Okay. So let's go with here. All right. So 1, 2, 3. Okay. Got a coordinate system there. We're going to consider. Let's consider these masses. 3-particle system, and one particle will be M1, and 2.0 kilograms, and it will be at position -1, 5, and 0.0. M2 will have a total mass of 5 kilograms. And this position is 3, 4, and 0.0. And mass 3 is 6 kilograms. And its position is 2.0, minus 2.0, and 0.0. All right. So let's go ahead and locate these particles over here. Now the object here is, find the center of mass of this distribution of 3 discrete particles. So the first particle is at -1 and 5. So that's going to be about here. -1 and 5 is up here somewhere. So there's M1. Particle 2 is so 3 and 4. So 4 comes out here, 3, so right there. And then particle 1, minus 2 and 2. So that's going to be right there. Now, each of these particles has a position vector, which we can illustrate thusly. Always love that word, thusly. Here you go. And that would be considered R1. It's a vector, so we'll put it in spectrum notation. R2 go. R2, and R3. Okay. Pretty two-dimensional system of particles. So, see if you can work on it. Take a couple minutes. See if you can apply this formula correctly. So essentially, this is what you're doing, right? And you're doing that for each one of these. So for example, XCM, it actually will look like this. So XCM is going to be equal to 1 over M, total mass, times basically R1, M1, plus R2, M2, plus R3, X. X1, X2, and X3. It's like you're adding up the components. Now, you could go in and do the vector analysis of it, but I've actually given you the values of the components, so you don't really have to even do all the drawing stuff that otherwise you would. Like if I didn't give you the values here, I would have to give you something like maybe the angle, and so you'd have to find the projections. But R2, basically X2 is equal to R2 times the cosine of whatever that angle is right there. So that's another way to approach it. But we've done vector analysis enough, so this really isn't about vector analysis so much as it is about understanding how this formula represents the center of mass and the components of the center of mass of this particle. So, but just keep in mind, you might see problems where it doesn't give you the values like I've done it. It gives you the angle and the magnitude of those vectors. So it just adds in another step where you have to do vector analysis on top of doing, applying finding the center of mass from the components of each. Valid. But here, this should only take you a couple of seconds, just a couple of steps. So go ahead and do that. But do me a favor, I want the answer in 2 ways. I want the magnitude of the resultant, and basically you can give the answer in 2 ways. The magnitude of the resultant vector and its angle, but you could also give it in vector form. So component form, that is. So determine, yes, let me write this out. Determine the center of mass. Determine the center of mass in 1 vector form or component form. Same thing. That is RCM. Basically, this is component form right here. And also give me the magnitude. The magnitude. So basically the absolute value of that guy, plus the times the and also the angle. The angle, it's reference angle, or as angle. So it's angle relative to the x-axis. And angle. So 2 different versions of representing the vector. Go ahead and work on that right now for a couple minutes. right back. Okay, sorry for the delay. Hope we got through this. Actually, yeah. So, right. So we can knock this out pretty quickly. I hope. So yeah. So axiom. Let's go ahead and start. Do it here. So just following this formulas, axiom is going to be equal to. So the total mass is, M is the total mass. The total mass is at 11, 12, 13. So 13 kilograms, so that's 1/13 kilograms times -1, -1 times the mass one, which is 2. So that's going to be minus. So yeah, we're still in stages. -1 times 2 kilograms. And of course, the 1 is in meters. So I'm going to multiply it out. See that? So -1.0 meters times 2.0 kilograms. Plus 5 times that guy. So that's no, sorry. Be careful, you got to go to the second term. So now 5 times 4. So, well, x2 is 4. What am I doing?
Wouldn't it be 3, Professor?
Yeah, 3, sorry. It's x, right? So 3, 3 meters times 5. So 3.0 meters times 5 kilograms. Then plus 2 meters times 6 kilograms. Thank you, DB. Yeah. And when you add all that up, DJ, what do you get?
I ended up getting 25/13.
Yeah, 25/13. And you can keep it like that. It's fine. You don't have to break it down. 25/13. And the units would be meters, right? Because kilograms cancels out. Cool. Yeah. So that's the first term. And the second term then would be, let's see who else. Mohammed, you want to give me that one? You there? So YCN, right? That's going to be 1/13. Go ahead, give it to me.
I'm not sure. Sorry.
Okay, so 5 meters times 2 kilograms.
Oh, 7.
That term.
Sorry, 10.
Yeah, for that term, I mean the whole thing. So you get the answer, the final answer.
Okay.
And then 4 times 5, so 4 meters times 5 kilograms. And then -2 times 6 kilograms. -2 meters times 6 kilograms. So that gives us a YCN of
so give me 1 second.
Sure. And while he's doing that, Shura, what is the Z coordinate? ZCN. Should be easy.
Okay, I got
0.
11.33.
Right. Okay, 11.33. That's not what I got.
Really?
It's gonna be less than 1. So It's 18 over 13 for this guy. 18,
Oh, 18
13.
over 13.
Yeah, right. Because that's 10 plus 20 minus, maybe you added that because it's a minus. So 10 plus 20 is 10.
Oh, okay.
Minus, is that right? Is it minus? Is that right?
Yeah.
Something's wrong. Oh yeah, minus 12. Yeah, so 20 minus 12. No, what? No, sorry, 30. So 10 plus 20 is 30. Minus 12 is 18, and then the 13. Yeah, so it's 18 over 13. Yeah, so I mean, you could do it in decimal. I mean, there's a couple of ways we could represent them. So then the RCM, you could write it like this. It would be equal to 25ths 13I plus 18 13ths J. And that's it, plus 0. So that's one way. In decimal form, you lose some information because you have to round off. But in decimal form, but that's a valid solution. Right? So but we want to kind of draw it over here. So I would probably convert it to decimal so I can get an idea of how to draw it. So that would be like 1.9I plus approximately, and then 1.4J. Right? So if I come over here and illustrate that, then this is giving me the coordinates. So my center of mass, so 1.9, that's almost 2 along the x-axis. So that's like here, and then 1.4, that's like 1.5. So probably a little bit less than 1.5. So maybe in here somewhere. Yeah. Okay. So the big center of mass is going to be that guy. So that's and that mass, so that's going to be 13 kilograms. So MCM is equal to 13 kilograms. And its position vector is going to point like the following, from the origin to that point. So that's RCM. Okay. So basically, once we get the center mass, we could effectively forget about all the individual masses and just look at how the center of mass responds to external forces. And since it abides by Newton's laws, that will give us an ability to approximate to predict what the system is going to behave, how the system is going to behave as time evolves. And so it's a very useful technique for figuring out this stuff. Okay, yeah. Now, that is for discrete system of particles, discrete system. When you have a continuous system of particles, it's really the same formula, but the mass becomes a differential mass element, and the summation becomes an integral. All right, so let's take a look at some problems like that and do a couple. Excuse me. What can I read? So I'll start here. So for a continuous mass distribution, and an example of a continuous mass distribution, a nice one would be this meter stick. This meter stick is a continuous mass distribution, and we can think of breaking it up into individual increments of mass, differential masses. And so if we add them up and find where the average value of the cinder is, well, you can guess what that would be, right? Where's actually, let me be careful. You have to be careful about that because this is relative to a coordinate system. So let's come back to this problem. Let me give the formulas up, and then we'll come back to show you that center of mass, the thing about center of mass is that it is not an inherent property of an object, right? It's relative to how you're defining the coordinate system. And that's a very, very important point to understand. It's defined by that R, and the R is always going to be determined by where you choose your origin. So unlike something like mass, which is an inherent, the mass doesn't change no matter where you are in the universe for an object. So it is an inherent property of an object or of a system. The weight, on the other hand, is not inherent to the system because it depends on the gravitational attraction, the external bodies nearby. So in that way, gravity is not, weight is not inherent to the object. So that's what I'm saying about center of mass. It's dependent upon how you define the coordinate system about which you're measuring the position of the various particles or parts of the system. So therefore, it can change center of mass based on how you define the coordinate system. And I'll show you that in a minute. First, let's get these formulas. So all of those formulas that we just said, they convert to integrals. Now, in physics, we can integrate, and here's where we start to get into a bit of a review of integration. Not really, it's more a practical application of what you've learned. In physics, we kind of generally oscillate between two ways we can integrate. The most favorable way is to integrate over the coordinate space, which is what you're accustomed to doing. But because we're applying this stuff to physical systems which exist within space, we also have the option of integrating relative to quantities associated with the system, in this case, mass. So we can integrate over mass, or and using differential mass element as the variable of integration, or we could convert that mass to how that mass is distributed over the space in which it exists, and therefore then integrate relative to the space using a quantity called mass density. So I'll show you what I mean. I'm going to write it down. First, the formula is down in terms of mass. Then I'm going to write it down in terms of coordinate by writing the mass in terms of the space that the mass occupies using the definition of mass density. So the basic definition for all those is just literally converting, as I said, the integral sign to the summation to an integral, and realizing that our differential masses now become, our discrete masses now become differential mass elements. So very easily, we would just write down the center of mass for the x coordinate would be 1 over m, the total mass, times the integral of well, it's not x sub i's anymore because now x is a variable. So it would just be x times dn. So this takes the place of the x sub i's, d sub i's, right? You see how that works. Same thing for the y's. ycm, it now becomes 1 over the summation of the integral of the y dy, y dn. And z becomes 1 over the mass, the integral of the z dn's. Okay. So we'll go with that, right? However, we can represent this another way, and this is the way that most books are probably going to do it. We'll start doing this. Yeah, so there is mass density, you know what mass density is, all of you know it, right? So mass density is mass per unit volume. Now you can have, as it turns out, in physics, we look at all the different geometries. We can do mass per unit length, assuming a theoretical one-dimensional system, like a string that has no width. We could do area, like, mass per unit area. In this case, though, we're going to be, most of these objects, we think about mass per unit volume, right? So in terms of that, right, because the mass of this pillbox, so to speak, right, it takes up a volume. Length times width times height. But because I defined mass density, the concept of mass density is that mass density is defined as 3 equal signs mass per unit volume, right? Then the mass is equal to the mass density times the volume, which means that if I look at a differential mass element, assuming that the mass density of the object is constant, like it is for this ruler, then that means the same amount of mass density resides in a differential element as resides in the whole thing or any portion of the system. So if the mass is equal to rho times V, then a differential mass dm is equal to a rho times a dV, a differential volume. Yeah. Now, how do I do this? Yeah, let's just go with that, and then we'll break it down for the various problems. Yeah, so if I take equation 3 and substitute it into any of these guys, then I can convert all of those to basically integrals over the coordinates. Now, oftentimes, now this basically implies a three-dimensional integration. Now, a lot of you might not have gotten to calculus 3 yet because it's not. So what we do in physics is we choose our differential element with high symmetry. So that, for example, if I wanted to do like a rectangular, well, we'll get into it in a minute. But the point is, just from a theoretical point of view, if I'm setting up my, I could break this up into the volume, differential volume into, well, yeah. So you know that volume is equal to, like, for a, let's say for a rectangle, assume for a rectangle. Consider rectangular symmetry. Right, then if I take a look at a rectangle like so, right? What I'm actually doing is breaking this thing up into differential elements like this, like that. And I'm looking at the RCM of each of those elements. So let's say that if I had my axis, I'll draw a three-dimensional axis like that. This goes along this axis, comes over here, right? So like, let's say this ith element over here, this differential mass element over here. That mass element, it's going to have a position vector R that's only one-dimensional. It's not three-dimensional. Like I can take it from here and, put my position vector pointing back to where that element starts. So basically my position vector is an X. And the thing is, each of the areas, not only of that differential element, but all of them, it has the same cross-sectional area, right? That area there is an area in the, if this is Z, that's Y, and this is X here. Actually, so let's make that X and that. So basically my position vector is along the Y-axis. So position vector would be along the Y-axis, but my cross-sectional area would be in the X, Z plane. And it would be constant. My cross-section area is the same. The face is the same for all of these elements. And that would be an area in the X, Z plane. So one thing I could do is realize that this differential element, only part of that is varying, just the part along the, in this case, Y direction. And so I could go one step further and break this differential element up into this following. It would be dm would equal rho times x, times y, which is the only thing that's varying, times a constant area that is the area in the xz plane.
And so therefore, rho and AXZ are constants, and they would come out of the integration. And so that's a way of converting a three-dimensional integral to a one-dimensional integral. Which would alleviate having to do the three-dimensional integral. Right? So that's the kind of thing we do in this class. So we're actually doing two and three-dimensional three-dimensional integrals, or whatever it's called, but we convert them using the property of mass density or charge density for next semester, and make it much more palatable. Not that three-dimensional integrals are that difficult. They don't have to be, but you know, if you don't have to do the work, you can be smart and choose the element based on symmetry so that you take care of those other two dimensions. So for this particular problem, if I did that and plug 4 into, and I guess really what I technically should do, I drew this wrong. I should have the origin so that it's in the center, not at the corner. But, you know, if I then wrote I guess I would have to use the YCM. So for this particular problem, oh, I didn't even put it in yet. So let me put all of them in. So let me rewrite all of those in terms of the coordinates, and then I'm going to put in that last step. So in terms of coordinates, or that is integrating over coordinate space dv as opposed to dm, then my xcm now is going to be equal to 1 over m, the integral of x times rho. In fact, let me go ahead and take the rho out. The rho would be over here because it's a constant integration. Rho x dv. Right, and this guy, YCM, would be rho over m times y d dv. And finally, z cm is rho over m times integral of z dv. But here's the thing I'm trying to say. Let's look at this guy right here. If I then take, using my symmetry, I can break up the volume so that it is only varying along one coordinate direction, not all three coordinate directions. So therefore, this dv would be the same as y dA, where a is a constant along the x and z directions. So this could be written as rho over m, and the a would come out of the integral. So it'd be rho times a, where there's a constant area along the x and z directions, times the integral of y dy. In fact, I left that, I said, yeah, that should be a dy, not a y, right? Because this is dv, dy. Right, because it's not, don't let that be confusing. Dy basically in Cartesian coordinates is equal to dx, dy, dz. It's a triple integral, right? But in this case, in fact, let's calculate the volume of that very quickly and show you what I mean. So if I were to calculate the volume of this thing, and let's say that well, you know, yeah, I could do it like that. So in this case, I guess the x-axis would have to go along this. Let me bring this all the way over like that. I don't know how you do it. Like, yeah, so maybe the x-axis would have to be coming along that direction. There you go. So let's say that it's a square A, right? So it's a cube, has length A and A. So this is A along the x-axis, and this is A along the z-axis, and the length is L. Total length of the thing is L. So the volume, we know just from our common sense that the volume of that cube is going to be A squared times L. So triple integral, this is how you would work it out. X-axis has to integrate from 0 to A. The y-axis integrates from 0 to L. The z-axis integrates from 0 to A. So it's simple, right? It becomes, the integral of x from 0 to A, L, so y times y from 0 to, sorry, x from 0 to A, y times y from 0 to L, times z from 0 to A. And in the end, you get A times L times A, which is A squared times L. Okay, fine, cool. That's all a triple integral is. Now, there's an easier way to do this thing though. And this is what I'm trying to say. This is what we do in physics. We take shortcuts. Check this out. If I choose using symmetry, if I choose my squares so that the area of the square is A squared, right? Then the area is the same on each one. And I can see that before I even do the integration. So as opposed to having to do the integration, what I'm actually picking out is an area. Basically, I could do this integral like this. It's going to be equal to the dx times the area along the x and y axis, x and z axis, excuse me. Because I can clearly see when I pick out my differential element that the area is equal to A times A. So it's a constant of the integration. That's what this term represents. So in this particular problem, AXZ is just going to be equal to A squared. So I take it out of the integration from the start, right? So then the volume, when I integrate both sides, the volume would just be equal to A squared times the integral from Z to, is that right? Yeah, so I'm integrating the y-axis, so yeah. So from y, so y goes from 0 to L. So it alleviates having to do a couple steps of, even though that was simple, but it gets more complicated when you get to more complicated, geometries or whatever. So I basically have converted the triple integral to an integral over one variable, and I get the same answer when doing less math. So we get A squared, right? And that integrates to y from 0 to L. And so my final answer is still A squared times L. So by being smart about how I pick out my differential elements, I can do less math. So that's basically what this means. I'm taking, I see that the area is rectangular shapes that I'm taking out. And so I can convert all of these problems to something like that. So over here, it would be rho times the total mass, but the area that I would take out here would be an area along if this is integrating along Z, the area would be along the XY axis. So this would be an area in X and Y times the integral of Z dZ. And this guy would be an area along the YZ axis divided by the total mass and the integral along the X axis, X dx. So this is really the way we kind of operate. And it makes, it allows us to kind of convert these things to triple and double integrals to integrals over a single variable by choosing problems of high symmetry. That's probably the first time you've seen something like this, but it's kind of fun actually once you get the hang of it. And I'm gonna do a problem right now to show you what I mean more practically. I mean, this is an example, but it's kind of a trivial example, so it might not be so obvious what I'm trying. You have to see it a couple times, and then you kind of get the hang of it. But these are the basic theoretical. So basically, you could do it like this, but we're going to be using essentially these formulas here to do the center of mass. More specifically, center of mass equals this quantity like this. All right, so let's take an example. And first, so now we can do the example of the ruler. Oh, we got break is time. We skipped our break because I gave you some more. But let me just set this up so you can do it over break, be a working break. Now, we're going to do this two problems, two ways. And first of all, let's figure out what the answer is before we calculate it, so we know what our answer is intuitively. The first step is easy. Oh, okay, if you mean like this guy? Doing it this way?
The one with the integration, the top one.
You think this is easier than this? That's what you're saying?
It seems easier. Yeah.
It's just because I mean, it's like 2 + 2 is hard when you're first learning. It's a different perspective. And yeah, it might be easier for this problem because this is such a simple problem. But as you get more complex geometries, you'll see that definitely learning this and understanding what it is, it's not complicated. I know it's just new, right? So it's a new perspective. That's what happens when you look at something from a different perspective. It might look like harder, but then as you get more experience with it and you start to do more complex problems, you see that it's actually easier using that new perspective than maybe something that you might be accustomed to. I think that's what I would say about that. But so let's take a look at this. Let's say that my coordinate system is such that the origin is the edge of this desk right here. So this is 0. So from that point up is positive z. Let's make the z-axis up. Out towards you is positive x, and along the corner of the stand is the y-axis, and of course positive y-axis. Of course, negative z down, negative x back toward the board, and negative y back toward, I guess, your left. Okay. So if I take this ruler, and let's assume so I take the ruler and I place it like kind of right there at the edge, so that the origin is here, and the total length of the thing is L, right? Now let's assume that it's kind of an ideal one-dimensional figure where either that or I can't really center it on the origin, but if I could put it inside, so that the center of the origin went right through the middle, maybe that's another way of thinking about it. I can't physically do that, but if I could superimpose it so that the y-axis went right down the center of the object, right? So that, so that it's centered, I guess, so that for x and z, the bottom of this edge here was at negative x, whatever it is, and the top is at positive x, and then for the width here, the thickness, that was, well, I guess that would be z and positive z and negative z, and over here the width would be along positive x and negative x. So those have I guess what I'm trying to say is if I did that, then y of xcm and zcm would be 0 because I centered the thing in such a way. So the only object would have the only component of the center of mass that would have a non-zero component is the y component. And if I called this initial position 0 and the final position along the y-axis, which you can't see, but let me bring it in here. If I call that L, then without even calculating this thing, we should be able to figure out where the center of mass would exist. The existing surviving component of the center of mass would be along the y-axis, and what would be the value of that center of mass if the length of the object is L? Anybody? Assume that it's a uniformly distributed mass over the length of this ruler. If it's lying along the y-axis, what is the position of the center of mass relative to the length of the ruler? It's not a trick question. Should be obvious if you think about it. Half the length, that's right. Good job, Dami. So in terms of my coordinate system language, the center of mass would exist at, if I wrote it out, it would be, for that problem, RCM would be equal to basically 1/2 L J, because the other components would be 0, right? So we know the answer. Now let me ask you something. What if I took the thing and shifted it so that 1/2 L is now at my origin? If I went through all the calculations and calculated the center of mass, what would be the value of my center of mass now? Dami, maybe you should go for it again.
Can you repeat the question, please?
Yeah, the question is so who said that? Roy. So I'm just asking, I take the thing and I shift it back so that L/2 is now at the origin. If I calculate my center of mass, what's the value going to be? And Roy, yeah, it would be at the origin, but what value is that then? 0. That's right. That's right. Now so you see, that's what I'm saying. Center of mass is not inherent to the object. It depends on how you're defining the coordinate system relative to the object. Here, the center of mass is L/2. But now in this position, you can think of it as changing the origin to the center of the object or vice versa. Either way, when you calculate the center of mass, it's now 0 for everything. 0, 0, 0, 0i, 0y, 0j, assuming that I was able to put it in the center again. So that's the point that I was making about the fact that center of mass is not an inherent property of an object. It changes, just like weight changes different places in the universe, but mass is inherent, so mass doesn't change. All right, cool. So now that we know the answer, let's do those problems. We know the answer, or let's do both of them. Let's first find the center of mass of that ruler if I place it at the origin. And I say ruler, it could be a rod. It's just to make it interesting. I've got a rod in my notes there. So let's make a rod. So like a cylindrical shape, kind of like the shape of my, the part of the shape of this eraser here, this cylindrical portion. And let me draw the picture, set it up so that it's set up so that it lies along the y-axis and okay, so draw my coordinate system here. Make it a 3-dimensional coordinate system. I'm gonna make it kind of go. How do I do this? Yeah. Okay, I'm kind of trying. Okay, I'll do it like that. Do something like this. Okay, so that's X. And that's Z. And maybe I make Y come out like, yeah, I got it. So I can do something like this, exaggerate it like that. So now Y is going to do this. Yeah. Okay, so X, that's Y, and this is Z. So if so now I'm gonna draw my, greatest artist. Yeah, we can do it like this. So I'm gonna take my my cylinder and I'm gonna put it here so that it's right up against the origin. But I guess I want to do it so that, yeah, I have to make that a dotted thing. So now I'm gonna project this back like that. This guy back like this. So here you can see it. But over here, I would have to make that kind of dotted because you have to see inside there. Yeah, that's gonna make it. Yeah. So it's kind of like, this is kind of our vantage point, kind of like this, kind of looking at it like from top down. So you can see maybe a little bit of the edge of the back there, but you can't really see the inside of that portion. So that's how we're setting it up. And the axis is like it's centered. So the y-axis comes out of the center here. So this really would be the y-axis. Maybe I should have that dotted to imply that it's on the inside, and then it comes out. Without getting too artistic here, I think that give you a good enough perspective. So at some point, then it kind of juts out from the inside. So I think it's centered on there like that. See that? I think it looks good enough. So now this position here is L. Obviously, this is 0, the origin, and it's not a one-dimensional figure. It's a three-dimensional figure. So this cross-sectional area here, you know, it's in the space, right? So it's a cylinder. Let's say that the cylinder has, and we can give the parameters. The cylinder has, you know, basically this would find the center of mass. This is how the problem would be written. Find the center of mass of a cylinder of radius, let's give it a radius of A, radius small a, and mass M, and length L. Length L. Length N, let's spell length, L-E-N-G-T-H, length L. Yeah, cool. So what we're doing is we're essentially breaking up. So, you know, we're applying this formula I just erased, but we're breaking up this thing into differential elements that have high symmetry. All right, so I guess here, the side view would kind of, you know, it's a three-dimensional view, but if I look at it straight on from the side view, it would just look like a block. And my differential elements would be like that. So the ith element here, that's what I was trying to show over there with the other thing. Its radius vector is going to be that guy, but that is y, and that changes. That's a variable. Like it's y for some particular value, y for this, but the next, you know, the next element is over here, and then that one, and then that one. So like, you know, what an integral is the same thing as what a summation is, but for a theoretical differential element. So this mass here is the dm. It's the dm, right? But it's distributed over the rho times a differential volume, with that differential volume being the differential volume being the dy, which is that differential length, times the cross-sectional area, in this case, which would be pi a squared for every one. So I just call it area. Yeah. So that's what we're doing. And so the formula then that we're applying is the one that we were just talking about. So in this case, I would say that finding the center of mass is going to be along the y. So it'd be like a, you know, basically you can see from symmetry, we can work it out, but you can see that z, like z cm equals x cm equals 0 because it's centered there. So the only one I have to really work out is y cm. And that's going to be equal to, assuming using the rho thing, rho over capital M, the integral of y, so the area is out there as well. So the area that comes out, this is, I like to put the subscripts to remind myself the dimensions over which the area spreads. So those that are the coordinate, the directions, which is going to be in this case, z and x. So a, zx or xz, y times dy. Yes, that's the problem that we're working out. Now, the area is going to be pi r squared, I guess. We could put that in, pi a squared for each one of those. So YCM then would be equal to, well, let me let you work it out. So in the end, you're just going to get a number. You know the number should be 1/2. So area is equal to, we could keep it as a constant, or we could put it in since I give you the values. The area is actually pi a squared. So we could actually put this in the center of mass in terms of the actual area would be rho. In fact, what we want to do is, I didn't give you rho, so you're gonna have to take rho out. So really what the problem that you're working is rho times pi a squared over the total mass equals the integral of y dy, where y goes from 0 to L. So that's what you have to work out. And the answer that you should get is L over 2. Yeah. So see if you can proceed and get the answer that we talked about. And then I would do the problem over again. Oh, sorry. This is going to be, yeah, that's going to be L over 2. And so then the other problem is that take the thing then and shift it. Take it and shift it like this so that the thing is halfway in between. There's your axis. So then shift it so that now the cylinder is centered over the thing like this, where this is now at position L over 2, and this is at position negative L over 2. And in that case, you do the same thing again, and you could, it's going to be trivial. Maybe I don't have to work it out, but if you work out the same integral, just like you did this, it actually now will work out that your center of mass will be equal to 0. All right, so let me let you take a break right now. I'm sorry to kept you so long. And then what time is it? Yeah, we got 30 minutes. Oh, wow. Oh, no, class is at 4:30, so you have plenty of time. Yeah. So I'll give you like take 15, 20, make it a working break. So you can work on this for 15, 20 minutes or so. Then we'll come back and clean it up. And then I'll move along. Maybe do another one for you. Yeah, sure. Why don't I do this? Got a little 341. What's the next stuff we got here? Momentum. Oh, yeah. So we're going to momentum. Impulse. Impulse. Yeah. And then collision. So we're going to collision. So, yeah, I think it'd probably be worth it. You got to give me a whole day to do that. Collisions. And then I don't know if I'm going to do the rocket problem this semester or not. I think so. That's my rotation. Okay. Yeah. So why don't I do that? Yeah, I'm gonna go ahead and do this other problem since it's kind of similar to this. So this guy, this is a cylinder, right? But what if I make it a cone? Like, I guess take out part of the cylinder so that we can keep it like this. This was kind of easy. Once you know what you're doing, like it's kind of easy. But this one, you can anticipate what it is without even doing it, right? But what if you made it like a cone of mass, uniform mass distribution? So it's something like this guy. It's not so obvious where the center of mass is, right? Something like that. So here you begin to see the advantage, and this was what I was saying earlier, Jesus. I'd rather not have to do a triple integral. You can, but it's definitely more work than choosing. Now, you got to be a little bit careful here because even in this one, when you choose your differential elements, the area does change. So you still got to be a little bit careful, but I think you can still convert it at least to a double integral. But I think there's a way to even, if you're clever, you can even convert it to a single integral. I think that's what I did in my notes. Let me show you. This really shows the advantage of this technique. So let me go ahead and, so I guess this would be,
Yeah, so you keep the mass the same. And the back area, the bottom radius would be this, so not there, because that radius changes. So I don't know. I think this has a certain name, foundational radius or something, or whatever, it'd be A. And it's a cone. So base radius A or whatever it is, whatever it's called. There's a specific name for it, I think. Let me get my tea real quick. Whew. All right, what you go ahead and start working on this one. I'm gonna set up and let you work a little bit on it. Let me set up for you. So again, I would start off with say that. Oh, sorry, wrong problem. I would start off with saying that so we're going to do this along. The center of mass for Z and X is going to be 0. So the center of mass is going to lie along the y-axis there. Now, so X, Y, and Z, and this is Y. So yeah, so we just start like we did before. I guess I did this 2 ways, didn't I? Yeah. Oh, it's actually really. Oh yeah. Okay. Oh no, right. Yeah. So here you go. So YCM is equal to 1 over m of the integral of y dv. But dv now. So here's the thing. Here's how you do this. The differential elements that you're breaking up, it's still going to be the same kind. Like, so we're breaking it up into differential elements like this guy right here. But now the radius of of each of those cross sections is not a constant. It's changing, and it's going from 0 when it's down here at a point to A, the radius. So we can still keep that in mind, right? So we're still doing y dv, and in this case, the dv though is not quite a constant. That dv is going to be whereas before. So the dv is going to be dy. Yeah, dy. Well, so we'll still have a y. But, so 1 over the integral m of integral of y dy. And the area of each of those things is still going to be pi, but now it's r squared, where r squared is a variable. Well, r is a variable. It's a variable. Now, yeah. So now I could again have that as a triple integral, but I'm going to see if I can figure out a way to convert that to a single variable. And you can do that by using geometry. Geometry is always kind of a clue in. So for the next step, we need to try to write the r here somehow in terms of y. Yeah. So that we can to convert to a single variable. So let's do that. So can we write r variable in terms of y to convert to an integral over a single variable? And the answer, of course, is yes. So this is how we'll do that. Let's take a side view such that we're looking down the positive x-axis. If we do that, what we see basically is a right triangle of the entire figure. Right? So we see something like that, where at every point, so this is like looking at half of the figure so this is the y-axis here, right? And this is the z-axis, and the x-axis coming out at us. Now, as I mentioned, we're breaking up our, I'll make it really thin. We're breaking up our differential elements into, disks that have a certain width. And so let's say that's one of the differential elements like that, right? So at any particular point, the radius of that thing is changing as I go up. So we can call that radius, that's what I'm calling R. So I'm just going to write R right in the middle of that. So that's R, that's changing. And Y at any given point, Y is going to be equal to the distance that I am from the origin. Sorry, not Y, yeah, Y. So that's Y, and both of those things are variable. And I think it becomes obvious from this how you would write R in terms of Y. So that's Y. Now, I didn't specify what this angle is, but I guess for a cone, you would specify it. Yeah, because that's something that would be known. The base radius, actually, you would know it anyway. You could figure it out, right? Even if I didn't give it to you, because I gave you L and I gave you A. So this distance right here is A, and so you actually know the angle, to be honest with you. And that total distance is L. So how could we express this angle? If I didn't actually give you the value of the angle, you could figure it out. If that's theta, what is the relationship between theta, A, and L? Anybody?
Sine.
Yeah, sine. So we know what the value of theta is. Sine theta, or theta, is equal to the inverse sine of A over L. So you know theta. So that means since theta doesn't change, these are all similar triangles no matter what position Y you are. So at this particular arbitrary value of Y and R, we still have it, right? We know that that sine theta is equal to R over Y. So Y is equal to R, sine theta is R over Y. So R is equal to Y times the sine of theta. And that's it. There you have it. So you could take actually this equation 1, 2, 3. So that's it. The only thing in here, see, theta is a constant, so y is the only variable. So if we take that guy and plug it into here, then we have the whole integral in terms of y, and we can integrate. So that's how you do it. Let's go ahead and plug that in then. So putting equation 3 into equation 1, then we get that YCM equals 1 over m of the integral. So I've got my y dy, got my pi, and then my r squared is going to be this thing. So r squared then is going to be y squared sine squared theta. Okay, so I can clean it up. YCM equals 1 over m. Taking my constant stuff out. Wait a minute, what happened to my row? Oh, what? Oh, sorry, folks. I messed up. That should have been a row in here because I went from. Oh yeah. There should be a row in here. So the initial one is YCM is equal to 1 over m of y dm. But when I substitute for dm is equal to rho dv. So there's a row here and here. I just forgot to put it in, and here and here. Yeah, so now I take the other constants out. So I'm going to have pi sine squared theta. So pi sine squared theta. All that stuff is constant. Then the integration is going to be y times y squared is y cubed dy. Yeah. It's going to turn out to be a pretty simple integral. One right? Yeah. Oh, wait a minute. Oh, Lord. What's wrong with me? It's not sine. Oh, my gosh. This is not right. It's not sine. It's tangent. Yeah, thank you. Oh, man. Who told me sine? Got me off track. Who said that? It's tangent. Sine is a over hypotenuse. But we're saying r in this case is, it's a and y. So it's tangent. Tangent theta is opposite over adjacent. So it's really tangent, not sine. Sorry, I didn't catch that. So tangent theta. Tangent. And tangent. Tangent. So I guess it's right in my notes. I guess I just didn't catch that. But good try though, good try. Tangent theta. Still, it's a constant, so it has nothing to do with integration. It's outside of integration. Okay, now, so we just integrate. So now when we integrate, so YCM is equal to all this. I'm going to keep all that stuff in parentheses there. So this is going to integrate to y to the 4th over 4, and it goes from 0 to L. So from 0 to L. So we just put that in. So YCM equals rho over m I think I got to take this call real quick. Hold on just a second. Sorry, folks. Oh, sorry, that was a call coming in. Sorry, I thought that might have been. Missed. I'm expecting something from FedEx. All right. Where are we? Yeah, rho pi tangent squared theta over m. And I've got a L to the 4, so times L to the 4 over 4. Yeah. Okay. So now what? So now I think it's just, so technically that would be an answer if you wanted in terms of rho, but as I said, by convention, we usually give center of mass in terms of, just in terms of mass. So we want to go back and oh, right. But I think we have to be careful because I actually don't know the volume of the cone. That we would have to calculate, right? Because we could do it real quick though. Rho is, the mass density is equal to the mass of the cone, which we know n divided by the volume of the cone. But I don't know the volume of the cone right off. Anybody? You could probably look it up in the table. Something like that is probably known. Anybody know it right off? Well, it's be a good, nice review of a triple integral for those who have done, like to show you. And those who haven't done it, it's not really a difficult thing. We would have to use cylindrical coordinates though. Turns out, let's just calculate it real quick, show you how to do that. So what we would have to do for the volume of the cone is basically what dv in cylindrical coordinates, and in rectangular coordinates is just dx, dy, dz. But in cylindrical coordinates, dv is equal to the integral of so one length, the length there would be like dy, so integral of dy. The z-axis would be rho. You have to, it's a rho d, it's a r dz, r dz. Actually, I'm using cylindrical coordinates, really is what this is. So cylindrical coordinates, you would have go out from 0 to L, and then the z-axis goes from 0 to A, but then you would have to spin that around the radial vector, the azimuthal angle, and that angle goes from 0 to 2 pi. So it would just be d phi. So that's in cylindrical coordinates, that's what it would be. Y goes from 0 to L, R goes from 0 to A, and then the angle goes from 0 to 2 pi. And so that just integrates, that becomes Y from 0 to L. This becomes R squared over 2 from 0 to A. And this becomes phi from 0 to 2 pi. Is that right? Did I mess something up? Oh, but I think you have to be a little bit careful too, don't you? Yeah, you do. Let's go ahead and do this. So I guess the last thing that I'm going to integrate then, the last thing that you integrate is the dy. Yeah, because the y is related to the r. So it has to be in this. So the way you would do that is handle these two integrals first. So this one and this one. So that would become integral from 0 to L dy. This thing here is just, so let me keep this one out. So I've already done those. Let me keep this one out for a minute because the r is dependent upon the y, so you just can't do them separately. So I'm going to leave that as a dy. So this will then become times, the way I have it here is basically a squared over 2 and then times the 2 pi. So that becomes 2's cancel. So that's just a squared times pi. However, then
Then R squared. Oh, is that a ratio? Yeah, it doesn't go. It's just take that from 0 to. Well, actually, I use a different. Yeah, this is a variable because I'm inside here. So, yeah. So as opposed, I'm sorry. Yeah, as opposed to making this a row R, I'm gonna make that like just a different symbol. Or I guess I could keep that R and make this something like a row. Something. It's gonna be varying. It's something that varies. So, yeah, I'm not. Yeah. I'll explain that. Well, I'll call that an A prime or something, meaning that it well, it's going to be square, so it's going to look kind of funky. Let's make it row. That's going to get confused with that row. So I don't know what to call it. Maybe I could just call it Z since I'm here. So to Z. Yeah. Pi is still a variable. So and that makes that Z squared. Okay. And then over here, so that's Z. Z. Yeah. Okay. Let's go back to this picture here. I need to make a little bit of a substitution in equation 10 over there. If you look at this, there's a couple of different ways I can manipulate this geometry. It's tan theta. Let's come back here. Tangent theta is equal to, let's call that 3a. Tangent theta is equal to r over y, right? It's r over y, but it's also equal to a over l. Equals a over l equals tangent theta. So maybe I will do this in terms of a because that'll help me convert it a little better. So let's say I went from 0 to a. So then I'll put a over here. So that you go back to what I had, a squared. But the problem is that I can't, these two integrals are related to one another. So I can't really integrate them separately. I have to integrate one and then use the answer of one as a variable to the other. And you can get it through this relationship right here. So before we used I guess we use ry is equal to tangent theta, but here I'm using that equation, that ry is equal to a over l. So that a is actually equal to, is that right? Tangent theta is, yeah. So what I'm substituting is it's dy. So I did that right. should be doing opposite over hypotenuse, opposite over adjacent. R over Y, A over L. What I need to substitute in for is R. Yeah, it's the other way around. So this is going to be a little bit confusing. It is a notation thing here, is what I'm calling. I've never really known how to write this, but I do it sometimes. I think maybe it's next semester. You haven't seen me do this yet. I guess, oh, this is why. I could just do this. So I'm using DZ, so technically the variable should be Z. So yeah, Z, like I'm in, like basically I'm on the Z axis, but at some arbitrary point, I'm going from 0 to the value Z. But then Z is also varying, so maybe that's how I should do it. So this is Z, DZ, but it goes up to R. I know it seems a little confusing because you can say, why does it go all the way to A? It's because this variable, these two variables, R and Y, are dependent upon one another. So I can't just go to the end and do 0 to A independent of that. I have to do 0 to R and then take the result of that and put it back into the integral for Y and then take Y to its final limits. And so here, that's what I'm essentially doing. And then I do that for every increment that I'm considering, every differential element that I'm considering. So this integral goes from 0 to R. So what I'm going to get is an R squared over 2, right? But now that R squared is a variable, and I need to write that variable in terms of Y, and I can do it here. So this is going to be R over Y is equal to A over L. So R is equal to Y times A over L, and it's squared. So then this becomes 0L dy, and the pi is still there. But R now, 2's cancel. The R now is going to be basically Y squared, and then A squared over L squared and times pi. So all the constants come out of the integral, and the constants are, this is still imagine. No, this is a volume. So this is A squared over L squared, integral, and the Y squared is in there, dy, and that goes from 0 to L. Yeah, that's it. And the pi is still out there. Got a little messy there, but I want to keep the cone up. So let's keep, let's take this out of the way. This guy, we probably want to keep that up too. So the volume then, equation 13, my final volume is going to, so Y squared integrates to Y over 3. So I have A squared over L squared pi, and then Y squared integrates to Y cubed over 3 from 0 to L, going out from 0 to L. Putting all that in, my volume is going to be, I just put the L in, so I'm going to have A squared L over L squared times pi, L cubed over 3, okay? So that gives me A squared. One of the L's cancels, or 2 L squared cancels, and I have 1 left. So that's going to be A squared. Basically, it'll be 1/3 pi A squared times L is the volume of this cone. Yeah. So that's the volume of the cone using a 3 a three-dimensional integral. And you compare that to the volume of a cylinder. You see, so the volume of a cylinder is actually pi a squared L. So basically, the volume of the cone is a third of the volume of a cylinder. It's interesting. So now you know. 1/3. Really? Not even 1/2? Wow. Why is it just pi? Did I? Oh yeah, okay. I'm thinking of pi squared. So yeah, okay. That's why it would be because it's not. If you think of the volume of a cylinder, is actually no, that's not true. The volume of a cylinder is pi squared. Is oh no, is no, it's a squared. It's about area of a circle is pi a squared. Yeah, pi a squared. So the volume of a cylinder is pi r squared L. So okay, yeah. So it is 1/3 the volume of a cylinder because the volume of a cylinder is this thing right here. Yeah. So it's 1/3 the volume of a cylinder. Okay. Seems like I knew that somehow. All right. Well, what we needed to do was to take this guy and put it into here. So we can just go ahead and do that right now. So I just put M over V, where V is this guy, into this equation. So we go ahead and finish this out. So taking equation 15 and putting it into 7, 15 into 7, we get that the center of mass is this equation 16. The center of mass in the end is going to be rho, and rho is going to be equal to the total mass over the total volume of the cone, which is 1/3 pi a squared L times pi tangent squared theta, and I still have an M over there, the M there. Now, but remember tangent, now I can use it, take it back out. Tangent is tangent, I guess, which one do I want to use? I guess I need to use, yeah, because we don't want to use the variables. So what I need to do is substitute in for tangent using this relationship here. So we actually ended up using all the relationships. Tangent equals R over Y, tangent equals A over L in this case, and also we just use R over Y equals A over L. So tangent is A over L, so tangent squared is A squared over L squared. So when I put that in, YCM is equal to, I can go ahead and cancel the M's, I guess, and the pi's. So that N cancels that M, that pi cancels that pi. And I've got 1 over 1/3 A squared L times tangent squared theta, and tangent squared theta is A squared over L squared over L squared. It looks off. The L's. Let me just keep going. I don't know. I don't want to erase that just yet. Guess I can erase this stuff. Okay. So the A squareds will cancel.
Professor,
Yeah.
on the tangent squared, I thought that if the square was like tangent square theta, I thought that would be squaring the tangent. Uh, you know what I mean? Instead of the ones that's on the inside. So wouldn't it not be like a squared L squared, but it would be something like tangent AL times tangent AL or something like that? Is that right? Or
So this is like three equations here. This is A over L equals tangent theta.
mm-hmm.
R over Y equals tangent theta. Actually, four equations, and then R over Y equals A over L. I'm writing them all together.
Okay.
So like the version in orange is just this: tangent theta equals A over L. So by algebra, if you square one side, you square the other. So tangent squared theta equals A squared over L squared.
Oh, okay. Okay, I got it.
And yeah. And also I see what I did. I substituted 15 into 7, but I left off this part here, L to the 4 over 4. So that's still there. Sorry about that. So that's in there. L fourth over 4. That came from this integration, wherever it is. I don't know, we kind of lost some steps. I guess it was, I don't know where it was. But so that's still over here. So that's what's wrong. Nothing's actually wrong, actually. It's going to work out. Yeah. So that's good. So any other questions? So you cool with what you were saying? You understand? Who was this talking? I didn't see.
Yeah, it was Roy. Sorry. What's it called? For the A squared L squared, I didn't catch it until just now.
Okay. All right. So I think we're good. It's going to get
Professor?
the answer. Yes.
I have a question. Equation 9, where the second integral that's integral of z dz. Why why did you change it from r to z the other time?
Because it's just a matter of variables. So like over here, I was using the r as a variable. Just because, I mean, I probably should have used z in the beginning. I used r because it's the radius of each of these differential elements. But since I set it up so that's the z-axis, each of those r values will have it basically has, the variable is really z, not r, based on how I set it up. Like that value here, the radius is a, sure. Oh, let me make it three-dimensional. Sure, it is, but still, it's going to have a value along the z-axis. So that, like, that's some value z. Then the radius for that would be some value z. Like, so it's really z that's varying, not r. You know, it's just nomenclature. That's all. I could have used z here. That's all. I could have done that, but I don't know. Somehow I started off with r in my notes. I think that's why I had it there. It's just a matter of nomenclature. Do you understand?
Yeah.
So this is a variable, and I could call it, you know, I called it r, but it's really a z. And that kind of confused me when I got over there. So it should have been z in the beginning, I guess, based on the nomenclature that I had chosen. But I put r initially because I know that it was varying along the z-axis the way I set it up, because I'm thinking that in my head. And then I came over here and I know I'm integrating along the z-axis, but I inadvertently put r down and then went ahead with the problem, but then I didn't have anything to call this up here. I called it a, and that was a mistake because I was going to the back here, the back of the maximum value, but I can't do that. I have to kind of take it inside before I get to there because that variable is dependent upon that thing. So then I was in a scramble, and it wasn't really the math or the physics. It was just that I had chosen the wrong names, and I was trying to figure out the correct name in a way that I wouldn't confuse you all. That's what all that mumbling was about. But it wasn't anything to do with the physics or the math. And then I realized it was an obvious choice that I had just messed up in the beginning. I could have just called it Z. So then that varies. And now when it comes to this point, I mean, I still like using R because it's basically Z and R because, you know, now it's a different variable that I can use, but I show that that variable is changing as Y goes from 0 to A. I don't know. That's all. It's just nomenclature. I hope that's not too much explanation. Do you understand?
Yeah. And the second question I wanted to ask, in that same equation 9,
Yeah.
the third integral, that was is that, I don't know what that variable
It's
is.
phi. It's phi. It's what's called the azimuthal angle. Phi, small phi, like in a Greek symbol. So this is cylindrical coordinates. In cylindrical coordinates, in math, you know, you have Cartesian coordinates, cylindrical, and spherical. Cylindrical are the second one. So it's like they use a cylinder to illustrate. So if I have a cylinder going around the z-axis like that, and then projecting down, I need to figure out something that represents every point in that cylinder, a coordinate system that would represent that. So basically, there is a radial vector that is perpendicular to the z-axis that comes out like this and represents a point on the cylinder. So that's making a 90-degree angle. That is a coordinate. That coordinate is people use either rho or you can use r. Here I was using r. So r goes from 0 to the maximum radius of the cylinder, right? Then you have the z coordinate, which goes from 0 to the maximum height of the cylinder. But then you have like if I project this thing down into the x-axis, I have the angle. You've got to spin that thing around 2 pi radians. So the coordinates in cylindrical coordinates then are going to be r for the thing that points from the z-axis out to a point. Z, actually the second coordinate is phi. Is what's called the azimuthal angle. It spins out. So that's the second coordinate, and it starts on the x-axis and spins all the way around in the xy plane. And then you have z, which goes from 0 to the height of the thing. Those are cylindrical coordinates. And as it turns out, so they correspond to x, y, z, but for cylindrical coordinates. And the dv, and that's something that you can actually calculate. So like dv in Cartesian coordinates is just dx, dy, dz. But in cylindrical coordinates, dv is equal to r, is equal to, what is it? It's r, or it's dr, let me get this straight now. Actually, it's rdr, dz, dphi. So that's volume in cylindrical coordinates. You can derive these things. That's part of calculus 3 to derive these, but you have to have an r in there. It's not just dr, it's rdr. And that's what this coordinate, so in my case, and that's also what was confusing me, is that my inclination was to use r, because when you see it in, cylindrical coordinates presented to you, they use r as that coordinate that goes from the z-axis to basically the a point along your object. And in my case, I flipped it to a different orientation. So basically, my r variable is along the z-axis. Like it's actually this vector here, but I've got it flipped around. It's like if I were to take my cone and flip it up like that, it would have the orientation of that. But everywhere here, my r variable is pointing from the origin to a point on my cylinder, making a perpendicular angle with the y-axis, where in this orientation, my r vector is still doing the same thing, pointing from the z-axis to my object and making a perpendicular angle with my Z-axis. So basically, in the Z in this picture is like the Y in this picture, and the Y in this picture is like the Z in this picture. But this picture is the way you're going to see it in the calculus book, and the way they lay it out. So that's what all that is. It was just me trying to kind of, since I had flipped my orientation, trying to make sure I wrote it down specific to the way that you normally would see it. And it was kind of confused because I don't do it a lot. I haven't done this in a while. So I had I was kind of rusty. That's all that was about. It was just trying to make sure I was writing it with the right way. And little things I was forgetting, like I always forget to put the R in there. And sometimes I forget that one integral is dependent upon the other. So, I was just a little bit rusty and trying to, yeah. So what calculus are you in?
2.
So you haven't done this yet then?
No.
Yeah. I mean, well, you'll see it. I mean, probably what I would do if I'm not actually making up a test. I don't think they're going to have problems like this on the thing I'm getting your test from. But like if I were making up tests and I would I wouldn't have you work on the volume. I would just give you the volume. And so then, you would have to do any of that. You would just take that volume and put it into the step that I'm doing. But I figured since we're doing it, and at least now you've seen it. So this is like in calculus class, when you get to this is going to be a pretty basic integral. It should be very easy. It'd be one of the first kind of things you might do. So since you've already seen it now, maybe just make that a little bit easier when you do see it. But you won't have to do that like this. This really got a little bit mathematical there. And normally, if I were actually doing this, as I said, I would probably just give you the volume of a cone, and then you would be using it in this other thing. But I didn't quite remember and whatever. I just was in a mood to do it, I guess. So any other questions? Okay, well, we're almost done. And I need that space, so.
Professor, I have a question.
Yeah.
Can you explain how you got equation number 16?
Yeah, equation number 16, I took 15, this guy, and put it into this guy, So I put the base, well, actually, that's not true. I put 15 and 8 into this guy. So it's 15 and equation 8 into 7. So the mass density is mass per unit volume. I calculated the volume here. So this first term right here is the mass density, rho. It's mass per unit volume. And then I have the pi, tangent squared, and then the L4 over 4. That's what that is.
Okay, got it.
Okay. It's not almost done. All the algebra is canceled out, and it's going to work out. So there's an L squared there. So I clean this up then. I have the YCN is equal to, so I have 1 over 1/3, which is just 3 in the numerator. I have L times L squared, which is L cubed in the denominator. And then I have times L to the 4th over 4. So that's L to the 4th over 4. Okay. Well, L cubed goes into L4 once. And my center of mass, YCM, is equal to 3/4 L. How about that? So 3/4 L is like, and that makes sense, doesn't it? Because when I had a cylinder, the center of mass was 1/2 L. But now when I make the cone, look at what happens. Most of the mass is down here on the right side. So it makes sense that it should shift the center of mass over a little bit. It turns out since it shifts it over 1/4 of the length. So 1/2 plus 1/4 is 3/4. That wasn't obvious to me. But before, so now it is, I guess. It's not so obvious. Maybe it would have been to somebody else. I don't know. But
it's not unreasonable that it's like a 3/4 is a kind of a quarter of it shifts to just a quarter of the length. So now if that's 1/2 L, then 1/4 L might be down here somewhere. I don't know. So yeah, it's a nice little problem to do. So that fits your intuition that you would think. Certainly you wouldn't think the center of mass should shift in the other direction. That doesn't make sense, right? Yeah. Cool. Well, that's center of mass. Yeah. I thought the square of a tangent is on the outside. Oh, we handled that already. Yeah. Why did you do X center of mass? Because it's 0 and the Y. Because I centered it, right? Like this thing is for the same reason that when I had the ruler in the X and Y was 0 so X and Z was 0 for the ruler as well. Like it's centered in. So like the center of mass is like along the Y direction. Where is the center? Where it's going to be 0. Z equals 0 along the vertical direction at any point, because it's the same amount of mass above the y-axis as below the y-axis. So for Z, that's 0. And the same thing in the x direction. Same amount of mass on one side than the other side as you go deep into the cylinder. So you don't even really need to do them. They're just 0 just from symmetry. Okay. All right. So keep reading this chapter. This is chapter 9 in your e-text. And we've probably done about half the chapter with this. And so the second half of the chapter is collisions. Collisions, inelastic collisions. And we'll be able to finish that on Wednesday, all of that. So we'll finish chapter 9 on Wednesday. We'll probably get into rotation on Wednesday too. So unless I do the rocket problem. I might do the rocket problem since we got rockets going up now again. We're doing space travel. I'll probably do that. Yeah, I'll do the rocket problem on Wednesday too. It's kind of fun. It's a long problem, but it's really nice to get through. So, all right. Yeah.
It's the test is going to be next Wednesday or this coming Monday.
So what I'm going to do is I decided to go ahead and give you a take-home test, so I don't have to spend time in class. So I'll open the take-home test on Wednesday, and it'll be on Newton's laws, and you'll have like a few days to do it. It won't be like give you some time to get it done. Okay.
Copy. Thank you.
All right.
Have a nice one, Professor.
Professor,
All right, you
I
too.
have another question.
Yeah.
On Canvas, on the calendar,
Yeah.
it says that there's 2 quizzes due tomorrow.
Oh yeah, I assigned a couple more quizzes. Yeah.
Okay.
They're short. They're five questions apiece.
Right.
You think you need more time? It's tomorrow night, so you think you need more time? Or
I haven't actually checked it out yet. I just saw it on the calendar. But if it's only 5, I think should be okay. I'll let you know if
yeah, you can write me and let me know. Yeah, I know I didn't have it all organized like that because we're still, but yeah, like I made them short, and I can't remember which ones they're on. Like they might be on I think they're probably, yeah, because I wanted to. They're probably on those on Friday. I think they're due. I don't know. I think I'd have to look at it. It might actually be the chapters 7 and 8.
All right.
But I gave you 4 quizzes: 4, 5, 6, 7, and 8. I can't remember the relative dates of when they're due.
Okay, for sure.
Yeah. All right.
Thank you so much.
Okay. Yeah, you too.
Professor?
Yes.
I have a question regarding it's something we did in friction. So I don't really take it back, but it's like I kind of understood it, but then like it was still kind of confusing. Like if a car is moving around a circular path, right? At maximum speed. There's a maximum speed where the car can reach before it leaves the racetrack, before the centripetal force stops acting on the car to keep it in that circular motion. And when the car is moving in that motion, the only force that's keeping it in is static friction, right?
Yes, that's right.
Okay, so if we had a question that was supposed to find the maximum velocity that the car could attain while the static friction was keeping it in, wouldn't that be will we use we'll find the net force that will give um, the mass time. Basically, we'll use Newton's second law, and then the net force will be the static friction because that's the only force that's acting that's the only centripetal force acting on the car, and then that will be equal to the mass times the centripetal acceleration.
That's correct.
So by doing that, we'll substitute the acceleration, the centripetal acceleration, which will be v squared over r. Then mv squared over r will be equal to the coefficient of static friction times the normal force.
Correct.
Okay, so in that scenario, we will be using, that's how we'll find the velocity, the maximum velocity that the car could attain, right?
Correct.
Okay.
Now, the problem that you do, it implies that it's a flat surface.
Yes.
In that case, the centripetal force would be equal to mu mg or mu n. If it's on a ramp, it's still equal to mu n, but n is not just mg. It's dependent upon the angle. But if it's a flat surface, then everything you said is correct.
Okay. What if the coefficient of kinetic friction was included in the question? Like, is there any will the coefficient of will the frictional force, the kinetic friction, ever be used like in the equation? Like, will it be used to like find anything in the equation?
No, they put it in there to confuse you. They put it in there to trick you because that force is in a different direction.
Yeah.
That force is anti-parallel to the velocity, so that's not going to contribute to, to the problem it's asking you about. Now, it might give you something else. They could ask you something else about what force is driving the car, but that's a whole different direction. So no, that kinetic frictional force has nothing to do with the centripetal motion at all.
Mm-hmm.
So if they added it in there, they're just trying to confuse you.
Mm-hmm. Oh, sorry, and one more thing. In that circular motion, is there a force that's pushing that's trying to push the car out of that circular path, or no?
So no, so that's the whole conversation that we had about centrifugal force.
Mm.
Like people who didn't before Isaac Newton, people said that there must be some force keeping it from doing that, because if the centripetal force is in order to satisfy Newton's law, and since the thing is clearly not moving in, or at least in their mind they thought it wasn't moving in, then we must have a force that's
pushing it out.
That's balancing that force. But in fact, it's a matter of perspective. The car is moving in relative to the central point. It's kind of harder to see it in that way, but they made the same argument about the moon. Like the moon is up in the sky, it's clearly not falling down. So, and we know gravity is pointing down. So to satisfy Newton's second law, there must be a force that's directly opposite gravity pointing straight out into space. Otherwise it would be falling down.
Mm-hmm.
But the fact is the moon is falling down. It falls down in a circle. That's what orbital motion is. So it's because
Here's what the problem is. You know that is equal to centripetal acceleration, but centripetal acceleration is acceleration. So if what the argument they're making is true, where you have an object that's not that's balancing the, whatever force is pointing toward the center of the circle, then that means that it wouldn't be the second law that defines the motion. It would have to be the first law.
The first law, yeah.
Yeah, and the first law says there is no acceleration, right? So you wouldn't have, like, in other words, acceleration can happen more than one way. It's not just a change in magnitude, it's also a change in direction. Uniform circular motion is a special case where the magnitude of the velocity is staying the same, but the direction is changing. So you definitely have to have an acceleration, which means the net force is not zero, which it would be if you had that other centrifugal force in the problem. So it would just be a complete violation of what's happening. So there is never a centrifugal force. It doesn't exist ever anywhere. We just keep the word, I don't know, because it's archaic. Maybe people just, once Newton came along and explained it, I guess the word was already ingrained in our language. So all those words where you hear it, like centrifuge in chemistry, or anywhere you hear a centrifuge, it's not real. There's no centrifugal force. It's just a word we still use kind of to describe motion like that, but it's not based on any real physics.
Okay.
So no, there will never be a force opposite the direction of motion in that way. No. I mean, let's put it this way. It might be for some reason, but it's not going to be, like you would have, like maybe you had some jets or something on the car that was pushing it out in that direction. I don't know. But if it's going in that direction, the net force is still going to be toward the center of the circle. Let's just not even go there. That's like some special case. I don't even know. Something like that I don't even ever even seen it exist, but I don't think it's impossible. But that still would not be a centrifugal force. It would just be some external force that's pointing in that direction. And the overall motion could still be in a circle, in which case the net force would still be toward the center of the circle. It wouldn't be a force canceling the force in the way that you mentioned. You know what I mean?
Yeah.
I'm trying to say, yeah.
Mm-hmm. Well, okay. What about in the case of like a string that has a ball attached to it at the end? Let's say the string is being moved in a circular, like it's being swung circularly, but in a vertical circle. Wouldn't gravity be acting on the, like if the ball, let's say the ball was attached to the string, and then the ball was at an instant the ball was facing down, wouldn't the force of gravity be acting on the tension? Because obviously the tension is what keeping it in that circular path. Wouldn't gravity be acting against the tension?
It would only be acting against a component of the tension. In fact, we did that problem in class. I did that. It was one of the first problems I did with centripetal motion, where I analyzed everything about it. So go back and look at your notes. You might not have been here or something, but I could do it really quickly right now. It would be against tension, but only a component of tension, not the whole tension. And the other component of tension would be the centripetal force. Can you still see the board all right?
Yeah.
Doing it turn light, yeah. Okay, so this is the vertical pendulum you're talking about, right?
Yes.
So here, yeah, and we're looking at a snapshot of the motion, right? So that's M, right? It's going around, spinning around like that. You got two forces on the thing, tension and gravity, right? So if this is, you would know the angle, you can define it relative to the vertical or the horizontal, whatever. Mm-hmm. So if that's theta, for example, then, this would be theta here. Mm-hmm. So if I did a free body diagram, I've got T, I've got mg, and I've got theta right there, right? So when I resolve my forces, So the tension, so I don't have to resolve this guy, mg, but here, that's going to be T cosine, no. Actually, you know what? Say again now.
The one that will be acting against gravity wouldn't it be T sine theta?
Yeah, actually, this is cosine, but it's because I defined the angle. Like in class, I think I defined the angle the other way. Like, and actually, usually in most books will do that. They'll define the vertical angle. So that's theta, and this is theta. That's why it's a sine. So in this case, this is actually the theta. So in that case, yeah, this would be T sine theta, and this guy would be T cosine theta. It doesn't matter. T sine theta is the same as T cosine of the complement of theta, which is the other angle. Yeah. So whatever. So yeah. So yeah. So in the y direction, sure, you have the net force equals 0, and so you have T cosine theta equals mg. So T or minus mg equals 0. So T equals. It gives you the tension. It tells you the tension is equal to mg divided by the cosine of theta. In the x direction, the centripetal acceleration is toward the center of the circle. So you have the net force equals mass times the centripetal acceleration. So the net force in that direction is T sine theta. So T sine theta equals mv squared over r, like you said, right? Where r is the radius of the thing. Yeah, and so then if I put this T in here, then I get basically mg times the tangent of theta equals mv squared over r. M's cancel, so that the speed is equal to the square root of g times r times the tangent of theta. So that's what the speed would be in terms of the radius r and of the angle that it's spinning. Mm-hmm. And so to answer your question, you were talking about gravity. Yeah. So you see gravity, tension has two components. One component balances gravity, the T cosine theta in that case, if you use that as the vertical angle. But the T sine theta is actually the centripetal force. Because that's always pointing toward the center of the circle as the thing spins around.
Yeah. So in the case where the circle wasn't horizontal, like the circle was vertical, like would it still be would the same thing still apply? Like we have to find the T component.
Yeah. So that's like if you had it on a flat piece of paper like that, and the thing is spinning around like this.
No, like upright.
What do you mean, going like that?
Yeah, like that.
That's still the case. That's a little bit more complex problem. That actually would involve integration. Now, what you could do is, because that's like a Ferris wheel or something like that. What people normally do is they'll just take out two spots. So like the top and the bottom. And they ask you to find like the speed at the top and the bottom or something like that. For a Ferris wheel. In this case, so that there the speed could be constant if it's a Ferris wheel. In this situation, if the speed is constant, the tension would be changing. But still, at this level, I think based on what we're doing, you would have to only do either the top or the bottom. Otherwise, you would have to kind of get into an integration as you go around. The velocity is changing actually as it goes around. But yeah, and so what you would do is, if you're at the bottom here, basically gravity and tension are in the same direction, right? Because tension would be down and gravity would be down. Here, gravity is down and tension is up. So that would be the difference. That's how you would get a difference in the, in fact, we could do it real quick, right? So assuming uniform circular motion, that the speed is not changing, and then the tension would have to be changed. So what is the, maybe you might ask, what is the speed of the centripetal force at the top? Well, centripetal force equals that. Yeah, probably like that might be what is the tension at the top? So call that T1 or T top and T bottom. Right. So at the top, so the net force is always going to be equal to mv squared over r, right? Where r is the radius of the thing. But at the top, you're going to have the two forces in the same direction. And they're also in the same direction as the acceleration, which is down. Right? Because it's centripetal acceleration is toward the center of the circle. So let me turn on the light here just so you can keep seeing it. A little dark there. So at the top of the circle, you have basically T top plus mg, because they're in the same direction, equals mv squared over r. And then in the end, the tension force is going to be equal to mv squared over r minus mg, which makes sense because, well, we'll see in the end. So the top, that's going to be the tension.
Yep.
At the bottom, the net force still equals mass v squared over r, but the forces are in opposite direction. And in fact, the tension force is greater than the weight. Otherwise, in the next instant, it wouldn't go up, it would go down.
Yep.
So the way I would write that is, because we always want to write the acceleration as positive. So I have tension minus mg is equal to mv squared over r. So in that case, T bottom would be equal to mv squared over r plus mg. So you can clearly see that the tension when it swings at the bottom is going to be greater than the tension at the top. Yeah.
Okay, that makes sense.
Yeah.
Thank you very much, Professor.
Okay. All right. Cool.
Have a good one.
All right. You have a good one. Be well.